Scattering experiments, especially scattering from crystals, they are important because they give information about the internal arrangement of crystals. So, last time we had a look at scattering of electromagnetic waves, high energy electromagnetic waves from crystals, and we had a classical electrodynamic treatment of the scattering problem. Today we're gonna have a look at the same problem in a with quantum mechanical perspective, and this gives some more insight into the problem and gives some quantitative um, explanation of the scattering experiments. These are the readings for this current uh, So going back to what we did last time was we had an incident electromagnetic wave with a wave vector k, and we were looking at what is the probability that you would see an interference, a constructive interference in a certain direction from the scattered waves. And of course, the scattered waves contain all the scattering from all the atoms from within the crystals. So, in which directions? So, specifically, we were talking about which directions would give you uh, constructive interferences and which directions won't give you constructive interferences. And that we did just by looking at the condition at which the phases add up, and at forward condition the phases just cancels out. Now we want to treat the same problem quantum mechanically. So what we do is, we instead of classical um, waves, we are now dealing with quantum mechanical entities. So we would represent the wave which is incident as by this cat, and the one which is scattered by this cat. So the incident field and the scattered field are now quantum mechanical entities. And now these are two different states, um, and so one state transforms into the another when this states interact with the crystal, and it interact with the crystal by a certain potential. And this type of potential would depend on the type of entity which is incident on the crystal. And this is something we will talk about a bit in the detail later on. But this is specifically the problem. You have an incident state and you have a possible final state, and this final state can be scattering in any direction, because so what you would like to know is, what is the transition rate from this state into this particular state given a certain potential of interaction. And so to treat this problem, we make use of something, a time-dependent perturbation treatment of a certain Hamiltonian, and that. So here we make use of a certain rule in time-dependent perturbative quantum mechanics, and that is called as the Fermi-Galton's rule. So consider a time-dependent perturbative problem where the Hamiltonian has a stationary part, which has a major contribution, and a perturbative time-dependent part. So this stationary part would give you some stationary states of the system, um, and such that uh, a discrete state I and a continuum of discrete states F. So these are set of stationary states. So normally under a stationary perturbation, there won't be any transition of a system from one state to another. So if the system is initially at one state, it won't go to this other state. But if you have something of a time dependence in your problem, for example, sinusoidal like potential, then you can have um, time-dependent interactions between these states such that a system which is initially in one state can transfer to another state. So the next question is, what is the transition rate of this uh, jump jump from one set of stationary states to another set of stationary state? So for such a sinusoidal perturbation, Fermi golden rules tell you that it is given by such a expression, where gamma, capital gamma I to F represent the transition rate from a certain initial stationary states to a final stationary states in the presence of time-dependent potential. Uh, and this is given by 2 pi by h bar, then a square of a matrix element. And the matrix element is the matrix element between the initial state and one of the final states. By the potential V, the square of it multiplied by a delta function, which is basically a resonance condition, where delta function is between the energy of the final and the energy of the initial state. So this would be maximum when the transition rate would be maximum when initial and final state have exactly the same um, energy, and that's kind of a resonance condition. So back to this problem. We have an incident state and we have a scattered state. And this scattered state is not one state, it can be many states. So this scattering can be done, can occur in a continuum of different directions. So and you have an incident field which is electromagnetic field, and it is incident on a potential, which potential is a periodic potential. uh, so is the interaction time dependent? So you can think about it this way, that this incident field, it is a time dependent field, and as it interact with a stationary potential, uh, and interacting this, the overall interaction would be a time dependent interaction, and Fermi golden rules hold. And it holds because the incident field is sinusoidal, which means that the time dependent perturbation due to the periodic potential would also be time dependent also, and sinusoidal. So uh, let's make use of the Fermi golden rule to find the transition rate from a certain state k to a later state k prime. And it's according to the Fermi golden rule, from k to k prime, the transition rate per unit time is given by such an expression, where this is due to this delta function is due to the resonance part. So if the energy of the incident and the scattered wave is similar, you would get a 1 over here. And that condition is satisfied for the case when you have um, something which is called as elastic scattering. So elastic scattering would mean that the incident wave and the scattered wave have exactly the same frequency. This is something which we assumed last time as well when we were treating this problem classically. Of course, you can have scattering in which the scattered wave have different frequency than the incident wave. These are called as inelastic frequencies, but at the moment we are not interested in that. But let me tell you that they are also very important describe very important phenomena, and inelastic scattering can give very valuable information about the sample itself. Uh, but let's have that discussion for some other time. So we are mainly concerned such that the case where the incident and the scattered wave has exactly the same energy. So this delta function give you a large value. So what are these states k here? So what I would assume here is to make the problem a bit easier. These states K represent the incident electromagnetic field. Let's say that incident field is inside the sample. So if let's say that field is inside the sample, I can represent that field by such a wave function. So of course this is understandable that it would have a traveling wave form, and a normalization constant 1 over L cube, where L cube is the approximate size of the sample itself. So if I consider that the wave is already inside the sample, then this would be represent a wave, the incident wave on the sample inside of it. And of course a similar k prime, which would also be inside the sample, will represent the scattering of this initial state into a certain final state. So this assumption is just to make the normalization easier. Otherwise you would have to normalize over the whole space. So let's look at this matrix element now. This matrix element, given such kind of states, is given by such an integral. So you have this k prime in the bra form, which represent a traveling wave, scattered traveling wave, and this represent the incident wave, and V of R is the potential, the periodic potential by which this crystal interact with these waves. You can take the normalization constant, and combining both these exponential together, you get such an expression which is given by exponent minus I k prime minus k dotted with R, where R is any position within the crystal. And of course you have a whole integral over this R within the volume of the sample, and V is the potential via which the incident electromagnetic wave interact with the crystal itself. So this is the form of uh, the matrix element which is here. And of course you, to find the transition rate, you have to find this matrix element, take the square modulus of it, and that would give you the transition rates of going from this to scattering in a specific direction. So we want to find this transition rate of scattering from this state to a particular state given by this, and the matrix element here is given by such an integral multiplied by 1 over L cube, where L cube is the volume of the sample. So if you look at this integral, it is a Fourier transform, and a Fourier transform of the potential V of R. V of R is the potential of the crystal itself. So this matrix element, it can be viewed as a Fourier transform of the periodic potential, where of course this potential has a certain periodicity, and the periodicity of the lattice or the crystal of the sample. And the Fourier transform is with respect to a wave vector k prime minus k, with or the difference between these two wave vectors. So this would tell you that okay, this scattering, this matrix element, the square of this, it gives you the scattering rate in a certain direction k prime, and this scattering pattern, it is a Fourier transform of real space. So what does it tell you? That whatever scattering you detect, it is basically a Fourier transform of the real space uh, lattice, or real space lattice potential. So that's why it justifies to treat scattering experiment as a experiment which probe the reciprocal space and not the real space. So let's look at this potential a bit more. You have this let's look at this integral. This integral, which is the Fourier transform of periodic potential, uh, here it is k prime minus k is dotted with a certain r, where r is any position vector uh, representing any point within this crystal of the sample. So you can do is you can take this origin at a lattice point. So this lattice point can be represented by a lattice vector then, and this position R can then be represented as a vector sum of uh, a lattice vector, a real lattice vector, plus an extra position vector x, where x start from a reference point on a within a certain unit cell. So uh, you can choose a certain unit cell, define a certain reference point in there, and that reference point has a certain position of itself. But that whatever position you want to describe within a unit cell, you can describe with respect to this s coordinate instead of an r coordinate. So this r position vector is now simply a vector sum of x and r. So that's why you can replace this r by x plus r and this r by x plus capital R and integrate it. So what I have done here is integrate over one unit cell here, where x is a position vector within one unit cell. And what you have to do is, if you have to describe this full um, integral, which is over it was initially over the whole sample. Now what you can do is you can do that integral in one unit cell and then sum over all the uh, unit cells, and that summation you can do by just simply summing over all these lattice, this integral over all these lattice points. So this is what I have. So what I have done is I have converted an integral over the whole crystal into a summation of integral over unit cells. This makes the problem a lot easier and tractable. So here you can assume now that you have a certain x. If you add a certain reciprocal lattice vector capital R with x, you would have exactly the same potential. So this is the property is that v of x plus r is equal to v of x. So this v of x plus r can be replaced by a simple v of x, and once you do it, you have a dot product here is in the exponential. So k prime minus k dotted with r, because it doesn't depend on x, and here the integral is upon x, so that k prime dot k minus k dotted with capital R can be taken out of the integral, and what you are left in the integral is something like this. Of course, v of x plus r is replaced by v of x. So this makes the whole uh, matrix element a lot easier to interpret. And let's see what does each of these two parts represent. So the scattering rate per unit time is given by this matrix element squared, and the matrix element is given by such an expression, given that this we have split the whole crystal into unit cells and integrate or uh, all the unit cells within the crystal. So let's look at this part first. If you remember, we have already seen such a summation previously as well in the last module. So if you define k prime minus k as another vector k double prime, then we saw last time that this summation, it gives you infinity whenever this k double prime is equals to g, a certain reciprocal lattice vector, and it gives you 0 whenever k double prime is not equals to g, where k double prime is given by this. The only difference between this and this sum over here is a minus, but you can appreciate that the minus and the exponent doesn't change this scenario. Only thing is you would have a minus g instead of a plus g. So uh, So this condition can be summarized in this statement that k prime minus k, uh, when k prime minus k equals to g as a reciprocal lattice vector, this sum would give you infinity. Otherwise, it would give you 0. This is called as a Lovey condition, which we um, derived last time as well. The only thing is now this thing is multiplied by a certain prefactor, so it won't give you infinity, but rather it would give you a large number. So this part of the matrix element, it just gives you some number whenever this condition is satisfied, and it gives you 0 whenever this condition is not satisfied. So what does it mean in terms of the scattering uh, experiment is that you have this state k, and this k can scattered into many different k prime states, but this condition would be only satisfied for certain specific k prime states, let's say the green ones here. So what does it mean? That this factor would be non-zero only for these specific scattering direction, and would be 0 for all the rest of directions, scattering directions. So that's what is meant by this first part of um, the matrix element. Now coming to the second part of the matrix element, which is this integral within a volume, within a unit cell. This is called as structure factor, or structure factor of a unit cell within the crystal, where x is a certain coordinate within the unit cell. This such structure factor is normally represented by an S, where S is a function of capital G, because this factors give you non-zero value only for k prime minus k equals to G. So for those values where k prime minus k equals to capital G, this factor would become capital G. So that's why this structure factor, it is a function of G. And for a particular set of G, we will know how to define G, which is uh, represented by HKL indices, and HKL indices multiply by these primitive reciprocal lattice vectors. It gives you your reciprocal uh, vector in, or reciprocal lattice vector in reciprocal space. So this S can be represented by a certain HKL index for a specific value of G. But we know that a specific value of G, or a specific G vector, or a specific set of HKL, it represent a particular family of planes. So what we can do now is this transition rate, which we defined earlier as a gamma. It can be transferred into something which is called as intensity of scattered wave, and the intensity of scattered wave would be non-zero only if this condition is satisfied, and the intensity amplitude is directly proportional to the square of the this structure factor, because this gamma, it does have a square of this matrix element, and because this is just a simple constant, we can say you can put a proportionality constant, and the intensity which is scattered uh, is directly proportional to the structure factor squared. But since this structure factor has a certain index, so for a specific HKL value, this intensity would represent scattering from a specific family of lattice planes, and that's how you can interpret this whole mathematics over here. As a very important statement over here, which we would use to identify the intensity of scattering. So just to give you a flavor of what all this means, so this statement, so you have a diffraction pattern made out from the scattered waves, and it looks like this. You can see the labeling over here. You have a central maxima which represent the case where you have unscattered, so this if the beam goes straight, and then you have these different peaks which represent uh, scattering from different planes. So, for example, this specific point would represent scattering from a certain plane. This would represent scattering from a 0, 0, 2 plane. This would represent scattering from 0 to 0 plane. And that's how you can represent, you can index this scattering from a crystal. Now you can see that this scattering, so with this, if you consider you have an incident wave which is going in this direction, then each of this point represents scattering at a specific angle, and this angle, specific angle, is given by this summation. And then you can see that some of these points are more intense as compared to other, and that intensity is given by this structure factor, or S square. So the larger this element uh, is, the intense the spot is, the smaller this element is, the less intense the spot is. So that's what this whole mathematics means here. So as we found out that the intensity of uh, scattered light or scattered wave would depends on the structure factor, and the structure factor itself is an integral or a unit cell, and it's an integral of a scattering potential. So, and you can also think about this structure factor as the Fourier transform of the scattering potential with respect to the reciprocal lattice vectors. So that's another way of looking at this problem. But anyway, so to to get the structure factor, you have to perform such an integral over the scattering potential. And we would see in the next slide what kind of different scattering potentials you can have. Uh, but to make this thing clear, the scattering potential has to be within a unit cell. So just to so what I have here is defined a unit cell, slightly different from here, but to prove the point. The scattering potential for the case of such a unit cell would be something like this. So you have a sum in this scattering potential, and this sum is over j. So the j is the number of unit cells within the some number of atoms within the unit cell. So let's say this for that particular atom, we consider um, it is located at a position xj, and it would have a certain potential given by v of x minus xj. Uh, what kind of potential we would see in the next slides, but nevertheless there is a potential correspond if an incident wave is incident on this unit cell and on this particular atom within the unit cell. This would be just the potential due to one atom, but then you can sum over all the atoms within the unit cell, and this summation is over all the atoms within the unit cell. So for example, if you have a BCC unit cell, would have to sum over two atoms, because a BCC unit cell contains two atoms or two lattice points if you have one atom on each lattice point. And an FCC crystal would have four terms in this summation. So once you find this potential, sum over all the atoms, and then you put that potential in here, do this integration, and you would get your structure factor. So now coming to the nature of the scattering potential, what kind of different scattering potentials you can. So the scattering potential, it depends on whatever is incident on the crystal itself. For example, until now we have looked at scattering of X-ray from a crystal. So you have an X-ray source which is incident on a crystal, a single crystal, and that produces a certain diffraction pattern. And the technique is called as X-ray diffraction. So the probe, the which is the entity which is incident on the sample or on the crystal is the X-rays, and they are electromagnetic waves. And the waves we use for such experiment have wavelength of an angstrom approximately, which corresponds to energy of a few tens of kilo electron volts, 12 keV for this particular wavelength, or 12.3 kilo electron volts. So this is quite a high energy. Let's say if you compare it with, let's say the binding energy of electrons to an atom. So yeah, so okay, so this incident probe, which is an electromagnetic wave, is incident on a crystal, and the crystal has atoms in it, and atoms have nuclei and bounded by electrons. So because this electromagnetic wave has electric part and magnetic part, the electric part of the electromagnetic wave can interact with the charges via dipole interaction, and so the interaction in this case is predominantly electromagnetic. And the interaction is with the atomic cloud, because the atomic cloud is surrounding by the is surrounding the nucleus. So the incident electromagnetic wave would see the electronic cloud and would interact with them and scattered off them. So, but this is not the only diffraction you have uh, for finding out the crystal structure. There are other diffraction or scattering um, uh, experiment which can be done to find the crystal structure, and one of the a widely used one is neutron diffraction. So in this case, what you have are incident neutron beam on a certain crystal, and you then record the diffraction of these neutrons from this specimen. Why we use neutrons? Because they are particles, but you know from de Broglie principle that a particle can be considered as a wave of a certain wavelength lambda. So if you know the momentum of the moving particle, which in this case is of neutron, you can find the lambda or the de Broglie wavelength of the neutron. And if the de Broglie wavelength of a neutron is a few is on the order of angstrom, which is basically the atomic spacing, then you can use these as well for diffraction from the atomic crystal. So in this experiment, the probe which is incident on the sample and which scattered off are neutrons, which are particles with a certain de Broglie wavelength, and de Broglie wavelength is on the order of 1 angstrom. And if you want a de Broglie wavelength of 1 angstrom, you need to give a certain kinetic energy to these neutron, and this is on the order of, like, let's say, a 0.08 electron volt for this particular de Broglie wavelength. What kind of interaction this neutron have with the crystal? So if the neutron are incident, the neutron are not charged particles, so they won't see the electrons, but they would interact with the nuclei within the crystal. So each atom has a certain nuclei bounded by electrons, and these in neutron experiment, the neutron would see the nuclei, and the interaction between neutron and the nuclei is a strong nuclear interaction. So it's not electromagnetic, but rather strong nuclear interaction by which the neutrons are scattered from the um, crystal. Then you have a third kind of widely used diffraction experiments. They are called as electron diffraction. And you might have guessed that electron diffraction have a probe given by electrons. So you have thermalized electron which are ejected from a certain source, incident on a certain crystal, and the diffraction. So the electrons are diffracted out of this crystal, producing some diffraction pattern which you can see. Uh, to create electrons of a certain wavelength, and in this case lambda of angstrom or so, then you need to give energy to these electron to have some momentum, and the kinetic energy which you need to give to those electrons is 150 electron volts approximately. This is a higher energy, which kinetic energy which you need to give to electrons as compared to the neutrons, because simply electron has a smaller mass than the neutrons. Of a neutron would have a larger momentum even with a smaller kinetic energy. So what kind of interaction does an incident electron has with a crystal? And you might have guessed, because electrons have charges unlike neutrons, so there would be electromagnetic interaction, just by Coulombic interaction, and it would be scattered from the electronic cloud surrounding the um, atom. Now we know that in different scattering experiment, the interaction or the scattering potentials can be different. So in case of an X-ray, the scattering potential is an electromagnetic potential. In the case of a neutron, it is a strong nuclear potential. In the case of an electron diffraction, it is an electromagnetic interaction. Again, so if you consider a crystal as made of nucleus and surrounded by electronic cloud, so you have tightly bonded electron and these valence or more delocalized electrons surrounding it. So that would how a crystal is made. And if you are an X-ray measurement in which X-rays are incident, so an X-ray would see a crystal like this. It would see the electronic cloud predominantly, and an X-ray would interact predominantly with this electronic cloud. So that's how it would see. The potential is a potential uh, centered on a certain atomic site xj, where xj may be representing the position of the center of a particular atom, and this potential is a spread out potential around this center of this atom, and the size of this potential is roughly the size of the electronic cloud. So that's what an incident electric field would see. If you compare it with electrons, incident electrons, if the incident electron is incident on such a crystal, it would immediately see this electronic cloud and would scatter from the electronic cloud. It won't penetrate much inside, but since X-ray have very large energy, much larger than the energy of the inner shell electrons, so these X-rays can really penetrate the electronic cloud inside. But an electron would just scatter off these valence electrons even. But nevertheless, the potential which you see in the case of an X-ray or the case of electron diffraction is a spread out potential roughly of the size of the electronic cloud itself. But a neutron, which is incident of the same sample, it won't see the electronic cloud because it doesn't have any charge. Rather, it would see this crystal as something like this. So instead of electronic cloud, it doesn't see electronic cloud, it just sees the nuclei via strong nuclear interaction. So for an incident neutron, the lattice would look something like this. So this is not a spread out potential, but rather a delta-like potential, such that you have a very interaction at exactly specific location of the lattice xj, so exactly at the location xj of a specific atom and not anywhere else. And you bj here would represent the strength of that potential, maybe, yeah, depending on uh, so different nuclei may have different strong nuclear interaction with an incident neutron, and that strength would be given by this quantity bj. So from this slide, or from these couple of slides, you might have seen that what kind of interaction you need to consider depending on the scattering nature of the experiment itself. So let's try to find out the structure factors. So now we have a better understanding of the interactions which can occur in different scattering experiments, and we would have a better understanding of what this potential would look like in these different scattering experiments. In this lecture, we would mainly concentrate on two scattering experiments, the neutron scattering and the X-ray diffraction scattering. So would start with neutron scattering because it's easier to describe. So in neutron scattering, you have a probe which is incident on a crystal, and that probe is an uncharged particle. It only gets scattered from the nuclei within the crystal and not from the electrons, and the interaction between the incident neutrons and the nuclei within the crystal is a very short range interaction, because strong interaction by nature is a very short range. So it's kind of a delta like potential. So You can imagine that if there's a unit cell, an incident neutron would only see these delta-like points exactly at the center of the atoms and not the surrounding clouds around it. So this interaction can be this potential which an incident neutron would see can be written as something like this, a summation. So you have delta like function as we saw here. So the potential is indeed at exact locations of xj's, where xj represent the location of the center of the atom within the unit cell, uh, and f multiplied by fj, where fj is something which is called as atomic form factor, and let's say fj would represent the strength of scattering of neutrons from a jth atom. So uh, because you can imagine different nuclei or different atoms have different size of the nuclei. For example, some may have smaller nucleon size, others may have larger nuclei, and a neutron would interact differently with each of them. So the larger, let's say, for example, naively one can understand that if a nucleus of a certain atom is large, then the neutron would scatter strongly with it. If it is small, it was uh, scattered, it would interact weakly with it. So this Fj is basically represent the strength of interaction of incident neutrons with that particular nucleus of atom J within a unit cell. And for the total unit cell, you just simply add over all the atoms in the unit cells. Now the question is, what is this atomic form factor? Uh, to find this atomic form factor, normally what's done is nuclei are separated and a neutron on incident on it, and the scattering of nuclei from a neutron is measured, and it is normally measured in terms of another quantity which is called as nuclear scattering length, represented by B. So for a certain atom J, this would be Bj, and this form factor can now be represented in terms of this nuclear scattering length, which is Bj, and the form factor will be simply given by Bj multiplied by this prefactor. So why we do this is because in the experiment, what is normally measured are Bj's rather than Fj's. It doesn't matter, once you find Bj, you can also find this form factor as well. So now this integral, this potential within a certain unit cell is a summation, and instead of fj, I have replaced bj over here and a proportionality here because this extra factor would add up. So it's not an equality anymore, rather it's just a approximate value. So the structure from this, you can put this into this expression to get the structure factor, and once you put this potential here, you get a structure factor like this, where the structure factor is simply by virtue of this delta function, you have an exponent eig dot xj multiplied by bj, where bj is the um, uh, nuclear scattering length for that particular uh, atom J or nucleus J in the unit cell. So that's the expression for the structure factor. This term would give you, um, uh, so you have some, this is, so we would have a look at what we mean by this full expression. And of course, you would have as many terms in this summation as the number of unit cells in here. And the meaning of this a particular exponent would become clear in the later slide. But important thing here is that this bj, which is the prefactor, and basically it determines the scattering from a specific lattice site xj. This scattering strength, it is independent or any other quantity, so it's a constant. So that's a very important factor to understand. And of course, the intensity from a specific lattice plane would be given by the square of this s factor, which you can calculate from the scattering potential. Now coming to the X-ray scattering, so incident X-ray, they interact can interact with the electrons because they have an electric field, and this electric field interact with electrons and scatter off those electrons. So naively one can understand that the scattering would be proportional to the electronic density. So if you, let's say, you can imagine electron density function such that uh, the density of electrons would be higher in the middle, in the center, and it would gradually taper off or decrease as you go away from the center of the atom. Um, so that's kind of a density function. And so if an incident electromagnetic field is incident on this atom within the unit cell, it would scatter off this density function. So the potential has basically the potential region is as large as the size of the electronic cloud, and the size of electronic cloud can be different for the different atoms within the unit cell. So naively one can understand that this potential, scattering potential of a certain jth atom, which is centered at xj, is given by two factor, uh, a function gj which is centered on that a certain jth atom, and it gives you the density of the electrons, of the electronic cloud within an atom. So that's a density function, roughly the size of the atomic cloud itself, multiplied by the atomic number of J, where atomic number simply gives you the charge or total charge on that nucleus, on that electron, on that atom, and specifically of the electrons in that atom. So the larger the atomic number is, the larger the negative electronic charge on that atom, and the larger is the potential. Similarly, uh, and then it matters on how the electronic cloud is distributed around that jet atom, so that these two the product of these two would give you the resultant scattering potential. So then the structure factor is given by you can find by putting this summation, this potential inside the structure factor integral, and then you sum over all the uh, atomic position within the unit cell. So J is summation over all the unit cells. Um, to make this integral a bit easier to understand, we can do integration, a substitution of variables. So you define a new variable x prime equals to x minus x j, and x, so this would give you x equals to x prime plus x j. So this integral, which is in this we replace x by this quantity and x minus xj by x prime, and this integral simply becomes an easier integral like this. So to bring this integral into the same form as we had for the neutron scattering, uh, we can now write this in this form. Just to let you know that you now have an integration in x prime, so it would just simply mean that you are defining a reference, your reference point, not at this location, but maybe another location within the unit cell. So this dummy variable basically doesn't do anything to the integral itself. It just changes your reference point within the unit cell. So I can switch back from x prime to x because now I have my reference not here but maybe somewhere else within the unit cell, so it just basically doesn't matter if I write prime with it or not. So this integral is simply given by this, and sum over j, where j is summation over all the atoms, and this summation I can now write in this form such that you have this factor multiplied by this structure factor, this form factor, atomic form factor, which we already had for the case of neutron scattering. So where Fj would represent the atomic form factor of the jth atom, and it would represent the strength of scattering from the jth atom within the unit cell. So some atoms within the unit cell would have stronger scattering from them, and some would have lower scattering from them. So for one which has stronger scattering, Fj would be stronger, and for the other, Fj would be smaller. But you can see here that this Fj which is the strength of scattering. Um, it is uh, proportional, it is dependent, it is not a constant value, but rather it depends on the reciprocal lattice vector itself. So in the next slide we would see. So this is the form of scattering potential you have for X-ray scattering. That's the scattering, the structure factor which you get, such that this quantity which is defined in this way in here. So by this, if you define Fj in this form, where Fj is a form factor, and you can see the form factor is just simply the Fourier transform of the scattering from the jth atom, of the scattering potential of the jth atom. So that's another way of looking at this atomic form factor, and this atomic form factor gives you the strength of scattering from the jth atom. It depends on G. So what do we mean by this? So G scattering can only be done when K prime minus K is equals to G, and this would occur, let's say, for a certain 2 theta angle. So when would G be larger? So you might have K prime direction, maybe in this direction, for which 2 theta would be larger, and for that the G would be a larger um, vector, in a vector larger in magnitude. So, or you can have a K which is very parallel, close to this K, incident K, and in that case, let's say K prime minus K would give you a small G vector. So the larger the deviation angle, the larger is the G factor. So what does this tells you? That this scattering strength, it decreases. So the scattering strength, it is a function of G, and with increasing G it would mean that the increasing scattering angle. So that's given by the x-axis here, which is sine theta by lambda. This is one way of representing the theta here. So the larger the theta, or in other words, the larger the scattering angle, the larger the G, and the smaller is the form factor for all these different atoms here, for silver, bromine, iron, and oxygen. So what does it mean for scattering? Experiment is, let's say you have this unscattered part, and then you have scattering at a certain angle, then there's a scattering at a larger angle, and this is scattering even at a larger angle. So this would represent a smaller, this would represent a relatively medium theta, and this would represent a larger theta. So as you can see, that as the theta is increased, the scattering intensity is decreased, and this might be due to the scattering strength, because the scattering strength from uh, specific atoms, it really depends on the scattering direction itself. So the larger the scattering direction, or larger the scattering angle, the smaller is the this atomic form factor, and the smaller is the magnitude of S, and the smaller is the intensity of the scattered light. So just to summarize, what we did in the last few slides is that the scattering intensity from a certain set of lattice planes, represented by a reciprocal lattice vector HKL, that intensity is proportional to the square modulus of the structure factor of that particular uh, Miller index. And the structure factor is given by such a summation, where the sum is over all the atoms in the unit cells, as we said before. And there are two factors in the summation. One is the atomic form factor, so where Fj is the uh, strength of scattering from the jth atom, and Eij or Xj is a phase for that particular atom. We would see in a minute what does that mean. So just to understand this xj, where x is a certain position, xj is the position of the um, a specific jth atom within the unit cell. This x is defined with respect to a certain lattice constant, and the coordinates of this x vector are along the coordinates of the real lattice vectors a1, a2, and a3, which in the case of, let's say, a BCC would be along these three edges. So this is these are the conventional unit cell lattice vector, and they are not primitive lattice vectors. So any xj would then be represented in terms of these three lattice um, lattice vectors, unit vectors, a1, a2, and a3, where xj would be the position of that particular jth atom along a1, yj would be the jth atom position along a2, and so on. So now here in this phase you have a dot product of xj with g, where g, so this xj again can be written in this form, so where x1 x2 represent one atom at the edge, and this represent the atom in the center. So this dot product is that with g and xj, where g is a reciprocal lattice vector of the specific lattice set of lattice planes represented by h, k, and l by these primitive unit vectors or unit vectors. They are not primitive, so unit vectors in the reciprocal lattice. So as we have seen that if you take a dot product of this, we can utilize this quantity which we have already seen. This dot product is the dot product of the ith unit vector in real space with the jth unit vector in the reciprocal space is given by 2 pi del ij delta. So let's say a1 dotted with b1 would give you a 2 pi, and a1 dotted with b2 would give you a 0. So this product is then simply dot product simply gives you 2 pi multiplied by hkl dotted with xj yj plus zj. Simple multiplication, not dot but rather a simple multiplication of these three with x, h with xj, k with yj, and l with zj. So that's what you get in this phase. And in the next few slides, we would do a few examples just to let you know what does these structure factors give, because these phase factors give, because these phase factors then determine whether you see any scattering from that specific set of planes or not. That we would see in the next few slides. So as an example, I start with cesium chloride, which is a primitive cubic lattice with a basis consisting of two atoms. So so you put a cesium atom at a lattice point, which in this case is, let's say for this unit cell is this lattice point, and you put a chlorine atom at a half distance away from the lattice point. So this would end up here, the chlorine atom. So the structure factor, or the structure factor for such a unit cell, would be given by the atomic position of these two atoms within the basis. Since this unit cell consists of one base, so you need to only define the lattice, only one lattice point, and that is a 0 lattice point. So with the 0 0 0, so you add a cesium atom at 0 0 0. So this would give you the position of the cesium atom, and you add a position of the chlorine atom would give you a half, and a half. These, as we said earlier, these are the position with respect to a1, a2, and a3 of the conventional unit cell. So the structure factor is then would contain two terms, one for cesium atom and one for chlorine atom. And for cesium atom, you have the atomic form factor of cesium, which would be different than atomic form factor of chlorine, because the cesium atom would scatter differently than a chlorine atom. Multiply by this phase, and in this case ei2 pi hkl dotted with 0 0 0, because that's what the position of the cesium atom is in the unit cell, plus the atomic form factor of chlorine multiplied by this phase factor, in which you have the atomic position of chlorine rather than cesium, which is a half, and a half. You do that dot product, what you get is this thing. You have cesium, this gives you 1 because e power 0 gives you 1. So you have the atomic form factor of cesium plus atomic form factor of chlorine multiplied by 2 pi I hkl by 2, hk h by 2 plus k by 2 plus l by 2. So you can take this 2 out, and their 2 would cancel with this 2, and you are left with ei pi into hk plus k plus l, and I pi is simply given by -1. So this whole exponent you can write in terms of -1 to the power h plus k plus l. Now the next question is, for what value of combination of HKL would this uh, um, uh, structure factor be non-zero? And the answer to that problem is that you can put any value of HKL, any combination of HKL here, and you would get a certain non-zero value of HKL. So which would mean that you would have some non-zero intensity for all combinations of possible HKLs over here, where HKL would definitely be in integers. So there's so a cesium chloride which has a primitive cubic lattice would uh, have uh, all the possible HKL points or reciprocal lattice points let's in the take the diffraction pattern. Example of sodium BCC now, which is has a lattice which is a cubic body centered, and it has a basis consist of sodium atom 0 0 0. So what you would do is you would take the number of lattice points in a BCC and put sodium atom at exactly at the location of the lattice points. So in this case, for a BCC, you need only two lattice points, the one at 0 0 0 and the one at 1 half 1 half 1 half. So at 0 0 0 you add a sodium atom to give you the position of the sodium in the one of the atom of sodium atom in the unit cell. And if you add a half uh, with 0, you get the position of the second sodium atom within the unit cell. So the structure factor would consist of, again, of two terms, one for one sodium atom, another for another sodium atom. And of course the atomic form factor in each case would be exactly the same because both of them are sodium atoms. Now, this phase, it would consist in one term of HKL dotted with a 0 0 0, which is this position. In this case, HKL dotted with a half, and a half. You can simplify this summation. This would give you the atomic form factor as it is. This would give you atomic form factor multiplied by this factor. So this is again -1 to the power h plus k plus l. So this whole term you can write in this form. You can simplify it further by taking this thing constant, and you have 1 plus -1 or h plus k plus l. Now this factor, this overall thing, it gives you HKL, the structure factor for a certain combination of HKL, and multiplied, which includes the atomic form factor, which would be, let's say, a certain number multiplied by this thing. So you can see the situation is a bit different now. What if you have h plus k plus l such that the summation and index would give you an odd number? So let's say I have h equals to 1, k equals to 1, l equals to 1. So that would be 3. This would become an odd number. So if it's an odd number, -1 to power odd number is -1. -1 with a plus would give you 0. So the structure factor would be 0 for 1 1 1, which is such that h plus k plus l is an odd number. So, and you can try for any combination of HKL such that the summation of HK and L give you an odd number. So for any combination of H plus K plus L, it gives you odd number, the structure factor would be 0, and it means that the scattering intensity from that particular set of lattice planes would be 0. So that's a very peculiar thing, and this absence of scattering from particular set of lattice plane. This is called a systematic absences, and in the BCC crystal, all those combinations of HKL whose sum gives you an odd integer, they are missing diffraction um, from the diffraction pattern, or their scattering is missing from the scattered intensity. So, and this would include, for example, a 1 0 0 lattice plane, a set of lattice planes. So 1 0 0 would be missing because the sum of HKL is 1, again an odd, and same would be true for these other two combination as well. So to see this, we can connect it to our previous discussion from the last Let's say we have this BCC crystal, and we said that the 100 plane scattering from 100 is missing. And the reason would be, let's say if you take a 100 plane like this in a BCC, it would miss the central atom in a BCC. So a 100 combination would not represent a family of lattice plane. It won't cover all the lattice points. So the important thing is scattering is that the lattice planes, a set of lattice plane which you are considering, should cover all the lattice point. A 100 is missing the central point in the BCC. Similarly, a 111 lattice plane would miss again the central atom. This set of planes would miss the central atom. So a 111 plane won't be a valid um, set of planes for a BCC because it's missing some of the lattice, one of the lattice points in a unit cell. So it won't cover all the lattice point and hence not be seen in the. So the systematic absences mean that these scattering represent those set of planes or those Miller indices which don't cover uh, we don't cover all the lattice points. This is again shown in this plane. So in a BCC, you can see that the 100 is missing, a 111 is missing, similarly a 210 is missing. So you can check any combination in which the sum of HKL is any odd number. It doesn't give you any um, scattering. So let's take an example of a face-centered cubic system uh, of copper. So you have a copper crystal with a lattice of uh, a face-centered cubic and a basis of copper atom at 0, 0, 0. So what you do, you take all the lattice points in an FCC, which are 4 lattice points, and then you add coppers at 0, 0, 0. So what you would get are these 4 atomic positions in a copper. So the structure factor would consist of 4 terms. So you can take the atomic form factor of copper common, and once you take it common, you are left with only these phase terms. So you have the first phase term, which is corresponding to this atomic point, the second one corresponding to this lattice point, and so on and so forth. This one, which has exponent as 0, would give you 1. This one would give you 2 pi h by 2 plus k by 2 uh, multiplied by 2 pi I. Similarly, this would give you h and L. This would give you k and L. You can simplify them like this, where 2 taken out, 2 cancels, you are left with these simple terms. So now what you have is you have this term, this summation of all terms, and you would find out that this structure factor would be 0 if all 3 h, k, and L are odd, or they are even. So unless they are even, so if all of HK and L, all 3 of them are odd or all 3 of them are even, you would get a non-zero structure factor. If you have a mixture of odd and even integers here, then you would get a 0 over here. So what it would mean that, for example, a 100 which has even integer and an odd integer, it would be missing in the scattering. Similarly, a 110 would be missing, a 210 would be missing, but then you can see that a 111 would have a non-zero, or a 222 would have a non-zero um, structure factor, and hence a non-zero scattering intensity. So again, just by looking at this plane, so you can these two have mixed odd and even, mixed odd and even. So these, both of these are missing in the FCC scattering. From a 111, which are again all 3 of are odd, is present in here. A 200 is present because 2 is even, 0 and 0 are even, so that's even. 210 would be missing, and so on and so forth. So so this is kind of just to summarize. So in a simple cubic system, you see all those different HKLs which are possible uh, in the uh, in the scattering experiments. Uh, in the body centered, some of them are missing, and particularly those whose sum is an odd integers. are would be missing. In an FCC, those would be missing in which all of them are either uh, if they have mixed order integer values. Um, and one can go on and do a similar subscription, a similar calculation for diamond and hexagonal structure, and you would find out other um, selection rules. These are called as selection rules because you select only a specific set of lattice planes and not the others. So in the diffraction, you only of a, let's say, of FCC, you would only see these particular lattice planes and not the others. So this is an important, these are important calculations because these gives you, so if you look at a diffraction pattern and if you see a specific lattice point missing, you can immediately identify uh, what kind of a crystal you are looking at. In this module, we had a look at a quantum mechanical treatment of scattering from a crystal, and we found out that the scattering intensity is directly proportional to the structure square of the structure factor. And we also looked at how to calculate structure factors. We also had a look at what kind of different scattering potentials can occur. And from calculation of structure factors, we found out for certain lattice systems or lattice types, some of the some scattering from some of the lattice planes or corresponding to the reciprocal lattice vectors are missing. These are called as systematic absences, and that's how you can define selection rules for either presence or absence for certain crystal systems, uh, for X-ray scattering and neutron scattering in general.